Okay, we're going to spend some time talking about radiation interactions and units of measure, how to measure this stuff, and we're going to get kind of a context around the measurement, because hopefully that historical context will help us understand the evolution of people's thinking around this stuff and where exactly we kind of can locate the snap where culture pivoted and said, oh, we're okay with radiation, to all of a sudden we're not okay with radiation, because that's a significant moment, right? And then it shapes a lot of what we're seeing in the hospitals is that pivot. So that's why I'm interested in the historical context. It's also helpful to have kind of a broad overview. So I don't expect us to know exact dates, for example, about when the Rankine was adopted as the unit of exposure. You do not need to know the exact date, but having a general decade idea, like 1930s, right? Helpful, very, very helpful to know where that is. So as I'm lecturing through here, I've tried to avoid specific dates in favor of general decade time frames, right? Because the point is not to memorize these historical dates. The point is to have some context with where radiation protection units came from and where they're potentially going. Because if we understand kind of the past, we can kind of see a little bit into the future and where we might be moving next. So here's some learning objectives. Can we read this? Is that readable or whatever? I'm sorry, the color kind of came off funny on these slides. But we're going to discuss attenuation relationships between radiation energy, site of interaction, and effect of radiation. You might be thinking, well, where was that in this reading packet? It wasn't in this reading packet, right? I assumed that we had some knowledge of photon interactions and that we retained that knowledge from physics and from CT. So I'm talking about things like photoelectric effect, Compton effect, pair production, photodisintegration. All of those things I'm going to brush on, and I've got a learning activity around them, and I know that there are areas that we continue to struggle in. Year to year, students struggle with retaining that information. So if you have struggled with it in the past, please go back in your reading and review chapter 3 in this textbook, or go back to your foundations or your physics book and review those reading sections on photon interactions, because that stuff ain't going away. And it informs a lot of how we think about stuff, but I don't want to spend an entire week just talking about photoelectric effect. I feel like we've beat that dead horse here within the curriculum. Does that make sense? Okay. Moving along, though, the rest of this material should be pretty much covered in this chapter. We'll talk about examples of early deterministic and somatic effects, late deterministic somatic effects, and stochastic effects of radiation exposure. That's kind of a review. We've already kind of discussed that to some degree, but those terms are not going away. We're going to drill down consistently deeper and deeper into those, because they do guide, at least in this chapter, they guide the evolution of these units of measure. We're going to differentiate the different radiation quantities and identify appropriate symbols for each quantity. And I expect us to do some calculations, right? We need to be able to calculate an equivalent dose, calculate an effective dose, calculate a collective effective dose, and then talk about why we have a TEDE, the total effective dose equivalent. Why do we use it? Where does it apply? And why do we come up with these numbers? So the first kind of big takeaway from chapter 3 or from your physics textbook is that we need to understand that, at least when we're talking about electromagnetic radiation, the energy of the electromagnetic radiation has a direct bearing on what type of interaction is most likely to occur, right? So this is a list here of energy increasing. As you go down the list, you see in kilo-electron volt, what the photon's energy is, it's increasing, right? And eventually we get into the omega electron volt range, right? And as that energy increases, the overall predominance of certain interactions statistically increases or decreases, right? And that's really, really important for us to understand. It's a critical thing. Like, for example, at energies, if a photon has an energy between 1 and 50 kilo-electron volts, it's most likely going to either coherently scatter, which means it interacts with the atom, and just moves on in a different direction. Doesn't necessarily ionize the atom, but interacts with it, moves on in a different direction, changes direction. Or it will photoelectrically interact. Then in that instance, it does ionize the atom. It produces an ion pair, and that fully attenuates the photon's energy. So the photon stops, right? In diagnostic imaging, we like the photoelectric effect, right? This is how we get X-ray pictures. So we are interested in photons that interact in that level of energies, right? So if you're an X-ray tech, you might be wondering, well, that says 50 keV. I set kVps that are much higher than that, right? 80 kVp, 120 kVp. But I want to point out to you the term is different. This is referring to the actual photon's energy. kVp refers to the kiloelectron, like the kilovolt peak. So what is the peak energy that could be possible in that beam, right? So this is speaking about the individual photons, that kiloelectron volt energy of that individual photon. So for the average beam energy, it is much lower than what the kVp is. So we use the photoelectric effect quite a bit. Now you'll notice as we go up in kiloelectron volts to the 60 to 90 keV range, we start to see falling off of photoelectric effect and an increasing of Compton scatter, right? Now we don't like Compton scatter in diagnostic imaging because Compton scatter just produces noise on our image, right? It is a form of attenuation. The X-ray has ionized the atom. It's moved on in a different direction. If that different direction is not incident on the image receptor, then in essence the beam has been attenuated. It's been stopped in a way, but it will go on to scatter. And I should point out that Compton scatter is the #1 way that we will be occupationally exposed to radiation as X-ray technologists. Compton scatter is the #1 way that you will be occupationally exposed to X-ray as an X-ray technologist, right? And that's coming off the patient. It's not coming out of the tube. It's not coming out of the table. It's Compton scatter from the patient's body. Now you'll notice once we get over 200 keV, from about 200 keV to 2 MeV, it's nothing but Compton scatter. Nothing but Compton scatter, right? So again, this tells us there's the ceiling for diagnostic imaging. We do not set kVps in excess of 120. Here's the reason why. If you go much higher than that, all you've got is scatter. All you have is noise, right? And potential occupational exposure. Now, where nuke med and our friends in radiation therapy come in is once we get above the roughly either 1.022 MeV, we have pair production, and that range from about 1 MeV to 10 MeV. We could actually produce pairs of electrons and positrons when the photon interacts with the nucleus of the atom. Kind of partially splits the atom, produces excitation sufficient to produce these pairs that are going to mutually annihilate each other, right? And that is precisely what we're doing in positron emission tomography. We are tracking pair production, right? We're using sufficient energy to produce pair production from this FDG that's tagged with some kind of radioisotope. I don't remember what isotope is it. F18. Is that fluoride or something? So radioactive toothpaste. They're putting radioactive toothpaste in you with a sugar molecule on it, and it's got sufficient energy in excess of 1.022 mega electron volts, and it produces pair production, and then we track the positrons that are produced. Now, I'm not going to get into the weeds of all that, but just know that's a crap ton of energy, right? So the reason I'm belaboring this point is super, super important for the folks in nuclear medicine and anyone who wants to use the PET-CT bathroom, right? As long as you stay away from the PET-CT bathroom X-ray techs, you can forget everything south of this, right? It is not impactful to your job, right? And it's not going to be on your registry except for as a distractor, right? It's only there as a distractor for your registry. nuke med and radiation therapy, you got to memorize them all, right? Because all these things happen in your course of work. Once we get over 10 mega electron volts, which we rarely practice anything in the hospitals that has energies at that level, we have actually photodisintegration, where we actually atomize portions of the nucleus, right? So as you can see, the top 4 are the ones they're most concerned with. If you're interested in more information, this is found in Chapter 3 in the textbook. If you need a reading packet, just shoot me an email and I'll send it to you. It's also available through the school library. So here's what I want us to do. So that is exactly the question here. How do we measure the different kinds of biological reactions seen after radiation exposure if the exposures themselves are theoretical, right? If we're saying it's all just theory, we have very little things that can measure this stuff. How do we know that any of this stuff is what's occurring, right? We see these effects in the presence of radiation, but how do we exactly measure it? That's kind of one of the big questions to ponder. We don't yet, and I'll tell you this, even though I'm going to lecture on it for the next little bit, we don't have all the answers yet, right? And chances are there's someone in this room who will contribute to our knowledge about it. The very first way that people measured it was a skin erythema dose. So from about 1900 to 1930, for about 30 years there, your dose badge were these guys. Right? You would walk around and you would take X-rays all day long, or you would be working on the cobalt machine or whatever all day long until your hands turned red. That was your skin erythema dose, and your dose monitor, your hands, had just told you you've got enough dose for today. Right? So that's what skin erythema dose means. One way to think about it is it's a tolerance dose. How much can this person tolerate before they need to take a break and come back tomorrow and their hands won't be red anymore? Now you can think of a lot of problems with this, right? I would hope. Number one, it's very unreliable. We have no way of knowing whose hands will turn red soonest, right? So let's say I work really hard in this department and someone else is kind of lazy and they like to put red paint all over their hands, right? And they get to go home early and have fun, right? That's the problem. Different people, and it really, anyone who's worked around radiation long enough will tell you it doesn't matter the color of your skin or what your gene pool is or what your gender is. It just interacts differently with different people. We still don't know why it interacts differently with different people. It is very strange. I have treated women and their daughters, right? And you would assume that the interaction of the mom would be very similar to the interaction of the daughter. They were completely different, right? Same radiation therapy treatment, very different interactions. Very unreliable, inexact, right? There's no way to measure the redness of someone's hand and say exactly, well, on Thursday my hands were this red. They were as red as Christmas. And today they're more kind of pinkish, like a flamingo, right? There's no way to chart that and say that this is an accurate thing. And then, of course, there's clear ethical problems with this. And, of course, that ain't all, right? So all we're tracking with the skin erythema dose is how red did your hands get, right? You do that long enough, and all of a sudden you're missing fingers, right? Why? Well, the excessive day in, day out occupational exposure that the early X-ray techs experienced, right, caused what we call radiodermatitis, right? So the repeated irritation of the skin, the repeated skin reddening caused something like hives, caused scarring, subcutaneous scarring. Eventually it could lead to necrosis, right? Because that repeated scarring, we have loss of blood flow to the skin, the necrosis sets in, and that's why these people are missing fingers, right? There's an additional scarring that was occurring on their hands. Their hands were getting very scarred, and they could not get sufficient blood flow to the extremities. So these are not mutations, these are amputations, right? They had to remove those fingers due to necrosis. So that would be one long-term somatic effect of radiation, but then we also have stochastic effects, right? Things like cancer and blood disorders. So they were just tracking it off of an early effect, skin reddening, with no mind for what long-term effects might follow from that. Okay, so this led towards some of the early investigations of radiation exposure. There was, in particular, some really high-profile cases of fatalities and things like that that also garnered the public's attention and the alarm of the medical community. Probably one of the earliest high-profile fatalities was Clarence Dally, who we can see here with Thomas Edison. Thomas Edison on the right is inventing a fluoroscope, and Dally has his hand on a wooden box within which is an X-ray tube, and they would sit there and fluoroscope Dally's hand all day long and work on this fluoroscope, right? Now, eventually Dally had sufficient repeated exposures to require amputation, and ultimately he died of cancer, right? His death was so painful and difficult for Thomas Edison to witness that he forswore any more experiments into X-ray. He did not do any more experimentation. So he discovered barium, he discovered radio contrast, iodine, and he also invented the fluoroscope, and he said no more, right? But this and other cases caused the medical community to say, okay, we need some way to have some guidelines here apart from skin erythema dose or some kind of threshold. So we have the creation of the British X-Ray and Radium Protection Committee in 1921. All you need to know is that this is the very first time that people sat down and said, hey, what's this stuff doing to people, right? And this is over 20 years after the initial discovery. So 20 years later, hey, what's this stuff doing, right? They did formulate some guidelines, but largely they were handicapped by a lack of accurate measurement techniques, right? Because we said that skin erythema dose was still being used until the 1930s. So we couldn't propose that. They needed something else. So the first definition that we had, or the first established quantity of radiation exposure, was the Rankine. And it came out of an evolution of things. So we have this British X-ray Council contributing to the first International Congress of Radiology in London 4 years later. And then the International Commission on Radiology Units and Measures also formed out of that meeting. And then we have the Second International Congress of Radiology. All we need to understand from this slide is that there was a building of interest around this stuff, and more scientists were coming together and sharing ideas. And out of that final Congress, they accepted the Rankine as the unit of exposure, right? The Rankine, named for the discoverer of X-rays, was determined to be the unit of exposure, right? And then the ICRU, the International Commission for Radiation Units and Measurements, was commissioned to define the Rankine. So we had determined what to call it, but we've not yet defined what exactly exposure is. And as you'll see, that search for defining what exactly exposure is difficult. But what persisted kind of from the 1930s on to roughly the 1950s, 1940s, was this idea of tolerance, right? That there's a threshold dose or there's a tolerance dose, and as long as you don't exceed that tolerance dose, you're okay, right? So it doesn't matter from one day to the next what you're being exposed to, just you have a daily tolerance dose. And so the U.S. Advisory Committee on Radiation, X-Ray and Radium Protection created these tolerance doses. Initially it was 0.2 Rankine per day in 1934, and you can see 2 years later they halved that, right? So it seems significant that already these scientists worked so hard to develop and define these units of measure, right, and establish what methods of radiation protection, namely tolerance, but already they're starting to question tolerance. Is tolerance overrated? So the search continues. And they also start to recognize that there are late deterministic somatic effects and late stochastic effects, like what we talked about with the amputations. That would be a late deterministic effect, right? And the stochastic effects would be things like leukemia, right? And they also start to suspect the possibility of genetic effects of radiation exposure, and this largely came out of experiments that were done on fruit flies, right? And without getting into all the weeds of all that, the scientists start to gradually pivot towards focusing on finding ways to minimize risk of sustaining damage caused by radiation exposure. So now is when we start to see things like collimators come onto the market, right? Tube housing, right? Ways to limit exposure from shielding. And the Rankine becomes internationally accepted as the unit of measure for exposure. So the Rankine is internationally adopted, and it becomes the first way that we have of quantifying what these theoretical interactions are doing, right? They're causing ionizations, and if you're exposed to enough of these ionizations, there's these potential effects that come out of it. Now the big kind of pivot, right? So the scientific community had already started to make the turn, right? But the world as a whole did not really make the turn or even think about this stuff until August 6th and 9th of 1942. Those are important dates, right? This is the one time I will quote an exact date and say that it's important. But August of 1942 is super, super important, because this is the dates that we dropped the atomic bombs on Hiroshima and Nagasaki and ended World War II. Now, what was so significant about this was the level of destruction that occurred, right, as well as the radioactive fallout. Those are two things, and they're very different. The level of destruction that occurred was caused by the intense heat that was released by these weapons. They burned roughly 10 times hotter than the sun. They were very hot, right? Incredibly hot. In fact, this is an image here on the right of, I believe, Nagasaki, and you can just see the entire ground is just burned. It looks like God put his cigarette out there, right? So, but in the public's mind, that heat that was released, right, was indistinguishable from radiation exposure, right? Because everything that I've just told you about radiation exposure, it causes redness of the skin. Well, if I get burned, that also causes redness of the skin, right? It causes people to lose their appendages. If they get scarred repeatedly, they'll have to lose their appendages. Well, if I get burned, I have to lose appendages, right? So the two things became fused, right? And I'm stressing that because it's probably the case even in your own mind to some degree. The legacy of this has gone down from generation to generation. It's been popularized in movies. It's part of the national discussion. And there's not enough people who necessarily have enough education to fully understand the distinction between the heat that came out of the reaction inside the bombs with the radiation that was released. They are two different things, is what I'm saying. And so we have to weigh them differently. In this class, I'm going to be focusing very much just on the radiation that was released by these things, right? And I would encourage you to do the same as well for this time. But this became the major pivot for when radiation protection kind of took the scene. And we see the production of signs, like with that classic propeller shape, the Geiger counter, the pocket ionization chamber, along with the uranium gold rush. People realized this stuff was weaponizable. It has there's a profit margin there. And so in the 1950s, you have uranium prospectors all throughout the western states looking for uranium in order to profit from it. But the main focus for us is that we see the beginnings of radiation protection. Another way to think about it is that, I like this idea of that we should have a low tolerance for stupid. So if this stuff is doing something, we can't measure what it's doing, why would we think that a tolerance dose was ever a good idea, right? Now you'll notice that the language is still there in things like thresholds, right? We still talk about thresholds. Beyond this threshold, we would expect cataracts to be produced. So we still have this language embedded in some of our thinking, but the pivot away from tolerance really happened after the use of the nuclear weapons, You have the development now of the National Council on Radiation Protection and Measurements in the 1950s, the NCRP, which is who I will quote over and over and over again. You'll notice they were all over your quiz, right? The NCRP Report number 116, NCRP Report number 160. And we also start to develop the international systems of measure, right? But what's interesting is tolerance died hard, right? I don't know why that's the case. I'd be open to anyone's theory. But in the early 1950s, we still have this idea of a maximum permissible dose, an MPD. That's not Memphis Police Department. It's maximum permissible dose, okay? And it replaced the tolerance dose, but if you think about it, it still sounds an awful lot like a tolerance dose, right? The tolerance dose was just saying this is how much you can tolerate every day, and the maximum permissible dose is saying this is your max, right? Don't go beyond this. So it's more of a hard break, but it still is, the tolerance is still kind of implied by a maximum permissible dose. We start to redefine the Rankine. We notice that we're on some shaky ground and it's not as perfect a unit as we had hoped. And so through the 60s, we start to redefine the unit of exposure. Which pretty much brings us up to modern times where we're at right now. The dose limits that we use, for the most part, were calculated and established in the 1970s, largely out of work that was done here in the state of Tennessee in what's called the Mega Mouse experiment, where they made a giant city of mice. Like, I can't remember how many tens of thousands of mice lived in this city. And they exposed different populations of mice to different radiation levels, and they figured out roughly how much radiation the mice could receive annually without there being any increase in cancer or genetic defects among the mice population. And then we took that number for the mice population and said that must be the same number for people. Now, I don't look like a mouse, and none of y'all look like mice to me, but just so you know, the 50 millisieverts annually, that is a mouse's annual occupational dose limit. We just incorporated it directly into human. So, lots of debate there still about whether or not that is an appropriate occupational dose limit, but those were calculated in the 1970s using all of that data. And the idea was that we want to make sure that anyone working with radiation has a job that we could call safe, and it would be equivalent to working at a desk, pushing papers. Unsafe occupations are things like underwater welding or lumberjack, right? If you're interested in safety, don't pursue those occupations. If you are interested in safety, X-ray, radiation therapy, nuclear medicine are considered safe occupations, right? The NCRP adopted the SI units for dose in 1985, but they've neglected to tell anyone else, including themselves, and they continue to use the traditional units. And the ICRP adopted the term effective dose in 1991. That became kind of ground zero for the most accurate form of radiation quantification that we have now in terms of interactions with people. The effective dose is now kind of the gold standard. So that was in the 1990s. So as you can see, this stuff is pretty young, right? We're dealing with a young science. Like I joked earlier about nursing, right, versus X-ray tech. Nursing's been going on for, roughly 6,000 years, I would think. Right, X-ray techs and dealing with nuclear medicine stuff been going on for about 100 years, right? Really knowing how safe this stuff is, about 20, 30 years, right? So this is still very much a new thing. And so what I'm saying is, even though you may be working in facilities that kind of have a safety culture of a certain kind, there's no way that all those safety cultures are correct. Not with something that's that new. Okay, so here's an overview of the quantities that are important. This is in our textbook. It's table 4-6. These are the ones that we need to know. We need to know them backwards and front and how they build off of each other. So we have a quantity of exposure. The SI unit is the coulombs per kilogram. It is measured in air, and it is a measure of ionization in air, right? And everything builds from that point towards that gold standard, the effective dose. Now, because, like I've said, here in America, we still like our feet and our miles and things like that. We still tend to use things like the Rankine, the rad, the rim, and the rim again, just because we're contrarian in that way. In fact, I got a dose report from Deborah the other day. I think it's still in rim, right? So even Landauer and dose quantification people are still using some of these units so that the hospital can determine what they want. But for the most part, the old school stuff can be forgotten. The registry uses all SI units now. When I took the registry, you had to know all the stuff about conversion and stuff. Now, we are still going to do some conversion. I'm still going to test you on conversion. The reason being you're going to be working with machines that still have junk reported in the old school way, right? You will still read reports and look at slides that have stuff in the old school way, and we need to be able to differentiate those two. But just so you know, if you're studying for the registry, if it gives you an amount in the SI units, it will also give it to you in the traditional units in parentheses, right? So it doesn't matter in terms of studying which you choose to study. You can memorize the dose units in the traditional, like the occupational dose limits. You can memorize it in the traditional. I would go ahead and save yourself the trouble, though, and memorize it in the SI. This is where we're at right now. We have exposure, again, like being coulombs per kilogram. We can talk about air kerma, which is a form of exposure. And we'll talk more about that here in a minute. It could be the gray. We can also, like I mentioned last week, build off of the gray to start talking about dose. So we can have gray sub A, which is an air kerma measurement, or gray sub T, which is tissue. That's dose, right? So the gray can do double service. It can be an exposure measurement as air kerma. It can be a dose measurement as absorbed dose. And then we have the two units that are expressed in sieverts, which are the equivalent dose and the effective dose. So let's talk first about exposure, because I've said that this was the very first concept that was defined, and it was first given the unit of measure as the Rankine. I'm going to give you a terrible, horrible exposure that I'm going to have to read because I've not even memorized it myself, of exposure. But this is the scientific definition of exposure. It's the total electrical charge of one sign, either all pluses or all negatives, per unit mass that X-ray and gamma ray photons with energies up to 3 million electron volts generate in dry, non-humid air at standard temperature, 22 degrees Celsius, and pressure, 760 milligrams of mercury, or 1 atmosphere of sea level, right? So what is this saying? It is super, super precise. Exposure, as it is currently defined, is just like, I don't know if you know, like in SI units, the unit of time is the second, right? And it's measured off of the oscillations of a single atom. And I don't remember even what the atom is. But they have a measurement that's measuring how quickly this atom oscillates. And that is the way that the second is measured. So what I'm telling you is, like Brooke Campbell has accused me in the past, if you ask me what time it is, I'll tell you how the clock is made, right? This is exactly that problem here, right? This is exposure, only I'm telling you precisely how the clock is made. Just know that it's super precise, and it's a measure of ionization. So if we're going to keep it simple, exposure equals number of ionizations. Now do not misread this simplified slide. It does not say exposure equals ionization. That's wrong, right? Exposure equals the number of ionizations. So underline number, right? It is the number of ionizations, and it is very precisely measured. The point here is precision, right? And you might be wondering, why do we care? Well, we're dealing with theoretical junk, y'all. So if we're trying to figure out what this stuff is doing, we've got to be this anal to understand if we're doing it right, right? We've got to be this worried about precision in order to make sure that we know that this theoretical stuff is actually doing what we're saying it's doing, right? So this is an example of the kinds of experiments that are done in exposure. It's a direct measurement, and it has to be done by an accredited calibration laboratory, right? when we're away from the laboratory, which is all of us every day of working in the hospital, we're going to work with instruments that have been calibrated based off of the closest laboratory, right? I don't know why I'm calling it a laboratory, but so annually or every 13 months, we're going to have to send our Geiger counters back to that lab, to measure it and make sure that this Geiger counter is still as precise as this measure that we have here in the controlled situation. So we have to occasionally standardize what we're doing or recalibrate what we're doing. The unit that we will use to express exposure is coulombs per kilogram, and it goes right back to that definition that I read you. The coulomb is a unit of charge. It only tells me how much charge something has. So how much negative charge or how much positive charge it has. And the kilogram in this instance is a volume of air. So how much charge is produced in a volume of air? That is exposure, right? The SI unit for radiation quantity exposure and is equal to an electrical charge of 1 coulomb produced in a kilogram of dry air by ionizing radiation. Now what's interesting about this is the SI unit's defined as X-rays and gamma rays. It doesn't say anything about particulate stuff. So we got to hold the phone on that. But we've at least got something that's helpful for quantifying how many X-rays we got hit with, right? We can convert it to Rankine if we're feeling bored. If I were to ask you a problem about this, I would tell you what the conversion factor is, right? You do not need to memorize this 2.58 times 10 to the negative fourth, right? Don't memorize that. But just know that the coulomb per kilogram is going to be much smaller than the Rankine, and that's intentional. It's more precise, is what this is telling us. That's all we need to get from this slide, is it's a very precise way of measuring this stuff. Okay. Sit with me for just a little bit longer, and we'll get out and we'll get up and walk around here in just a sec. Okay, air kerma versus exposure. So we have an SI quantity that can be used to express radiation concentration that's transferred to a point, and that point could even be the surface of the patient's body, right? So the skin. That is what we're talking about when we talk about the air kerma. Now, just for confusion's sake, kerma means a lot of different junk. I always think about Kermit the Frog every time I see it, but I have not yet come up with a mnemonic that's helpful, right? But just know that it could be kinetic energy released to matter, kinetic energy released to material, kinetic energy released per unit mass. The important thing is that we're trying to say exposure, exposure, exposure up to some point where it's actually interacting with the surface of an object, right? And the reason that's important is because it ties into what we're driving towards, which is that effective dose, right? So exposure up until the surface of the object. So we use air kerma, and it's probably going to start to replace things, or something like the air kerma is going to start to replace stuff like the coulomb per kilogram, just in terms of general usage of calculations and understanding interactions with tissue. Now, what's interesting about it, if we're going to break it down into its component units, it's joules per kilogram. So remember, the initial unit of exposure that we had was coulombs per kilogram. All we did was just switch the coulombs out with a joule. A joule is the unit of work, right? So if you stay with me, it's interesting because the coulomb means so much charge has been produced. And now the joules per kilogram is saying how much work can that charge do, right? How much work is going to do on a biological system. So this is what we're talking about when we talk about the gray. The gray is the joules per kilogram, right? Now what's nice about the kilograms in this instance is we can say a kilogram of what, right? A kilogram of air, a kilogram of tissue, a kilogram of what, right? So that's why we have, if it's air kerma we're talking about, it's going to be gray sub A. It's how many joules of work are done in a kilogram of air, gray sub A, right? If we're going to use it to talk about the amount of work that's being done in a mass of tissue, it's gray sub T. And now we're talking about how much tissue, a kilogram of tissue, right? Now, one really tricky thing, and this is a place where some people like to write tricky questions, and I wouldn't put it past the registry on this, right? If I'm talking about the absorbed dose, or the air kerma for a volume of air, if it receives X amount of gray, right, that volume of tissue or that volume of air, the entire volume has received X amount. I can't subdivide it. If I say how much did half of it got X amount, right? The X won't change. So if I say it got 10 gray, right? The air got 10 gray. Well, how much did half of that volume of air get? It got 10 gray. How much did a quarter of that volume of air get? It got 10 gray, right? I could keep subdividing it into smaller and smaller volumes. It still all got 10 gray. Now, that doesn't make a lot of sense to me, but that's how this joker works, right? Again, we're dealing with theory here, and that's just the way that we've defined it. I'm not going to get into all the weeds of why that's the case, right? Now, once we have that air kerma and we've said that we can define it for air or for tissue, we can start to distribute it out over a surface, right? And that's what we're doing when we do a dose area product. This will probably continue to evolve, especially in diagnostic imaging, as a kind of gold standard. Because what it does is, we looked at the sum or a version of it in CT when we talked about things like the DLP and the CTDI, right? We're saying how much dose was distributed over what area of the patient's tissue, right? So we're quantifying it across a volume. So it's the sum total of air kerma over the exposed surface of the patient's body. And we normally express it in milligrays per centimeter squared, right? Why? Because that is an area measurement, right? Centimeter squared just means what's the area. And this is actually really helpful. It's something that could be reported very easily, and actual dose could be calculated from a DAB. But probably the more important thing for us to understand right now is just the absorbed dose, right? The absorbed dose is expressed in gray sub T. If it's being abbreviated, it might just say gray, right? It might just say GY. Know that that's an absorbed dose, right? If the T isn't specified, it's implied, is what I'm saying. If the T isn't specified, we're talking about people, then it's talking about an absorbed dose, right? And it's the quantity of or amount of energy per unit mass absorbed by the irradiated object. Now, if I'm looking at a patient now, and I say this patient got 10 gray to their hand, and I decide to cut off their finger, and I say, how much did their finger get? It got 10 gray. And I decide to cut off just the tip of their finger. How much did the tip of their finger get? It got 10 gray, right? So that same theoretical whatever is there even with the patient's body. It's responsible for any biological damage resulting from exposure to the tissues from the radiation. And this is the part that I find tricky about the fractionating of it, if you will, is that some structures in the body can absorb more energy than others. Number one is the bones, right? So it doesn't make any sense, from my point of view, to say that it all got 10 gray when the bones are absorbing more of it than the soft tissue, right? But that's where we're at. We're working from that point. But as I just mentioned, the amount of energy that's going to be absorbed is going to vary by the structure, and it's specifically its atomic number, the mass of it, how big the person is, right? The energy, how much energy does the incident photon have, and as well as anything else that might be going on, like we mentioned, iodine contrast, prosthetic, things like that. But at the end of the day, that absorbed dose measure can be expressed in gray. We can convert. This is the conversion process here. It is a helpful conversion to know. It's also helpful to know how to do subunit conversions like we've already talked about in this class, right? So if anyone feels like they're on shaky ground on that, we're going to be continuing to look at that with our math packets. The easiest way to remember all of these conversions is 1 rad, the old traditional way, equals 1 centigrade. If you remember that, you can do all the other conversions as well, because 1 rem equals 1 centisievert, right? 1 rad equals 1 centigrade. Now, we have some other things that I think just for added confusion, we decided to throw the SID in there, right, the surface integral dose. It is similar to the DAP, and it was previously known as an exposure area product. It's just yet another way to try to quantify what was the surface of area that was exposed to the radiation. So I just don't want people to get confused about that. All right, let's take a little break. Okay, the important thing here is in thinking about linear energy transfer, we kind of have our answer for why we've had to be so general about things like the air kerma and the dose area products. Because these things are doing really weird stuff inside of people's bodies, right? Stuff that seems kind of counterintuitive. So I'll point out the one thing that is a major trip-up point for me, and hopefully it'll help y'all. Generally, we think about the linear energy transfer as the LET. We will be returning to it, so if you don't catch it this time around, it's not going away. We'll come back to it. But it helps us explain this need for a modifying factor for different radiation types. So the W sub R, or the radiation weighting factor, is a dimensionless quantity that's going to come out of our understanding of what we just saw. That when we roll an alpha particle across the thing, it's going to hit a bunch of stuff. And it may not get very far, but it's going to knock a bunch of stuff out of whack while it's doing it, right? Versus if we roll an electron across the table, it's going to get really far. It may only hit 1 or 2 things, but it's going to keep on going, right? So that alpha particle, in this way of thinking about things, has a high LET. It has a high LET. It gives off a lot of energy as it's traveling across the surface. That's what that linear energy transfer means. As it's traveling, it gives off a whole lot of ionizations, right? Versus a photon or an electron, these smaller things have a low LET. Now the problem with that is they travel further, right? Now our demonstration wasn't exactly perfect, but it definitely showed that the electron, if it had sufficient energy, could keep on traveling, right? The alpha particle would give off a whole lot of ionization and ultimately stop. So this is the point of confusion that students commonly have, is that radiation with a high LET transfers a large amount of energy into a small area. Therefore, it can do more biological damage if it's inside of someone's body, right, than low LET. But low LET travels further, right? So don't be tripped up by that. The high LET does not get as far, but it does a lot while it's getting there. The low LET goes really far, but it doesn't do as much ionization. What we're saying another way is source matters, right? So whether the X-ray, the radiation ionization, the exposing event was an alpha particle, beta particle, which is an electron, a neutron, or a photon, that's important, right? That's important. So we have to have a way to quantify that. And we're recognizing that we're not perfect, but we can at least be thinking separately. So we can say, in other words, like 10 gray of X-ray to the hand is different from 10 gray of alpha particles to the hand. In fact, it's a lot different. It's a lot different. So we quantify that with these numbers here. Just know that if I ask you a problem that requires a radiation weighting factor, I will give you the weighting factor. So if it's a calculation problem, I'll tell you, for example, the weighting factor for alpha particles is 20, right? At the same time, I expect you to understand that these weighting factors vary based on the size, right? So you might get a problem saying, which of the following weighting factors is most likely an alpha particle? And hopefully you will pick the largest weighting factor, of the ones that are listed there, right? Because that's the big takeaway here, is that these weighting factors equate exactly to not only size, but to that linear energy transfer. So we need this in order to quantify or calculate an equivalent dose. It's a dimensionless factor, and we'll use it, basically we just multiply it to the gray, and the outcome is the equivalent dose in sieverts, right? It's the equivalent dose in sieverts. This places the risks associated to biological effects on kind of a common scale. Sometimes we also call it a quality factor. In fact, your CT textbook refers to this as a quality factor. For the most part, though, I will refer to it as radiation weighting factor, or W sub R. So now that we've talked a little bit about linear energy transfer and how source impacts biological response, we can think about an equivalent dose. Sometimes it's abbreviated EQD with a tiny q for some reason. This is the product of the average absorbed dose and its associated radiation weighting factor. Okay? We're just going to take the absorbed dose in gray and multiply it by the weighting factor. So the weighting factor for X-rays is 1. So if my hand was exposed to 10 gray of X-rays, my equivalent dose is 10 gray. All I did was take the 10 sieverts, I'm sorry. I took the 10 gray, multiplied it by the weighting factor of 1, and I got 10 sieverts. Okay? It's more helpful when we're looking at various types of radiation exposures to a single population. Here's the formula. The equivalent dose equals the dose times the weighting factor for the radiation. So the dose will be expressed in gray. The weighting factor is a dimensionless unit. And the end result, the equivalent dose, will be expressed in sieverts. This slide comes directly from the textbook. It's just talking about how we could calculate an equivalent dose for exposures to various types of things, right? So they got 0.1 gray of X-ray, 0.05 gray of neutrons, and 0.2 gray of alpha particles. And all they did was they took those different dose amounts, multiply them by the appropriate weighting factor, and then summed everything, added everything together, and that final equivalent dose is expressed in sieverts, right? So you can see the dose in sieverts is much higher than the dose in gray. This person only got 0.35 gray, but they got 5.1 sieverts. So when we equivalate across all these different sources and we're thinking about the way the alpha particle knocked everything around, the dose went up. Okay, but we don't just have random atoms inside of a patient's body. We've got different types of tissues. So I alluded to earlier that tissues with a higher atomic number attenuate more radiation, right? But also some parts of the body are more radiosensitive than others, right? So things like the gonads, the lung, breast tissue, the bladder, they have a higher radiosensitivity. So not only do we need to think about a radiation weighting factor, we need to think about a tissue weighting factor, right? And so what we're driving at now is towards that effective dose where we can actually calculate how this radiation affected the patient's body and all the various systems it interacted with, right? So this is trying to account for the risks to the entire organism brought on by irradiation to all the various tissues inside the body. And what we're talking about is an effective dose, sometimes written as capital E, lowercase f, capital D for some reason. And this provides a measure of the overall risk of exposure to ionizing radiation. Translation, this is the gold standard, right? So we've just spent a lot of time unpacking how it works. The big takeaway here is it's important, right? This is a very, very significant thing. Now, you might not think about it as being a significant thing, and that's fine. I would probably challenge that, though, because if we weren't able to accurately calculate an effective dose, we wouldn't know what CT pictures look like. We wouldn't know what a radiation treatment plan means. We wouldn't even know what a PET CT scan is telling us. Those images and that data and those plans all derive from being able to calculate this, right? So the fact that we're able to represent those things as different attenuation values is implied by this, right? So it is the sum of the weighted equivalent doses for all irradiated tissues and organs, and that's from NCRP Report number 116, which hopefully by now looks kind of familiar. It's the occupational dose report. So this incorporates both the effect of the type of radiation and the variable radiosensitivity, right? Is it radiosensitive or more radioresistant of the organs and different parts of the body? And we will use this to determine overall harm to the person. This is the way it's calculated. We will have a dose that's in gray, an absorbed dose. We will multiply it by a radiation weighting factor for any radiations it might have received, and then we will multiply it by all the tissue weighting factors. Thank you. Okay. So that is how an effective dose is calculated. If you're given a problem where you've got a bunch of different types of radiation and a bunch of different types of tissue, just know that you need to multiply that dose by the various radiation types and the various tissues and then sum it all together. It's pretty evil. I will not ask you those kinds of problems very often. Just know that this is why the physicists get paid the big bucks. Here's what I'm saying, though, from our textbook. You can see they've got, all they were able to calculate was alpha particle effective dose to the lung, right? So you can see as we get more granular with this, as we try to break it down to the smaller and smaller levels, it gets very difficult. And now we're actually saying, right, that this was just to the lung. I'm not telling you what happened to the chest. I'm not telling you what happened to the bones. I'm not telling you what happened to the heart. I'm just talking about the lung. So the millisieverts are your friend. Anytime we do an effective dose and equivalent dose calculation, the outcome of that will be a millisieverts. We barely ever express something in centisieverts. It's generally sieverts and millisieverts. And the reason for that is most medical procedures, we can quantify them fairly easily in millisieverts, and anything that will kill you, we can quantify in sieverts. And we generally don't do things between there, right? We don't give away our sieverts for free, right? So if we're hitting you with some amount of radiation, we're either trying to help you out or we really, really don't like you, right? So that's why we generally only express it as millisieverts or sieverts. Millisieverts mean we like you, sorry this had to happen. Sieverts means we want you dead, right? So in general, you only need to know how to convert between sieverts and millisieverts. So you might be wondering, what are some application points for this? Well, this is calculation for how to know what happened during a lumbar spine examination. If we have a dose area product, we're able to kind of quantify what parts of the patient's body interacted with the radiation or vice versa. We can calculate, for example, a fetal dose with some accuracy, right? And we can make predictions from that calculation. All right, there's two more units that we need to think about. The first is the collective effective dose. I think it's always just called the collective effective dose. I don't think it's shortened. I could be wrong. But this is what we have when we look at that pie chart. The pie chart from NCRP report number 160 was based on a collective effective dose of the entire U.S. population, right? So we've just zoomed out to the 10,000 foot level. Earlier we were looking at what's this stuff doing at the atom level, what's it doing if I change up the source, or if I'm irradiating a kidney versus a lung. Now we just zoomed up to the 10,000 foot level and we said, what's it doing to the United States of America, right? That's a very different question. So we need a slightly different unit to think about that. And the unit that we use is called the Person-sievert. So now we're thinking not only about the radiation exposure, we're thinking about the exposed population, right? Radiation exposure to a certain population. So we use this for epidemiology and things like that, huge population studies of radiation exposure as a way to determine how this thing affects, for example, heritable risks from reproduction within a population, as well as what kind of the average exposure was for an individual within a population. And that's generally the way that we think about it. We're either using it for reproductive risks or possible cancer incidents, so epidemiology, or we're looking at what's the average. What did the average person get due to Chernobyl, for example? And we'll express that in a Person-sievert. So here's an example of a way that we might think about that. If there were 200 people that received an average effective dose of 0.25 sieverts due to like a dirty bomb or something like that, we would be able to quantify their collective effective dose as 50 Person-sieverts. We just multiplied the two things together. And then we could average that out. We would know, well, we know from this that it's already told us an average, but assuming we didn't know an average, we could figure one out. This is the number one way that it was used, is NCRP Report number 160. And it's not going anywhere, y'all. You might as well memorize some of this stuff now. It's important, right? The big ones here are the radon and thoron is 37% of the collective effective dose, right, percentage-wise in 2006. Computed tomography was 24%, right? Everything else is kind of small compared to that. Nuclear medicine's half of CT, right? And things that the general public feels really afraid of, things like nuclear weapons or nuclear power, those are the little tiny things right here. Like here's industrial right here, right? And industrial would include nuclear power and military uses of radiation, right? So it doesn't even, it's a less than 0.1%, right, of people's average exposure. Now that could increase, right? You have a nuclear war and that slice is going to get really big really fast, right? But I bear in mind the number one thing that's going to come out of a nuclear war is heat, a whole lot of heat. So you got to worry about the heat first before you ever worry about what this pie chart is doing. The final unit that's going to be helpful for us is the TEDE, or the total effective dose equivalent. This is used in radiation dosimetry, and it's defined by the National Regulatory Council to monitor and control human exposures. So they describe this as the sum of the effective dose equivalent from external radiation exposures and a quantity called the committed effective dose equivalent, the SETI, from internal radiation exposures. Why do we care, right? Again, this is just another way of quantifying it across a population. Different science groups will use different things to kind of do similar work. It's just what they've standardized and what they've determined is what they want to consider. So the nice thing about the SETI is or the TEDE is it's designed to take into account all possible sources of radiation exposures. So even things that we didn't normally think about. And we use it for dose monitoring, things like occupational exposures, right? So it is part of how we go and we set occupational dose limits. We calculate a TEDE. So in case you're wondering, this is all the conversions. I've just put it all in one slide. It is helpful to remember that 1 gray equals 1 joules per kilogram, that the coulombs per kilogram is a unit of exposure, and that the sieverts can be converted into different stuff. All right, thank y'all.